welcome to the Bodhi Academy. My name is Amsha Plaso, and in today's video we will learn about Chemical Kinetics chapter 3 class 12. So in previous video we learned about the factors influencing the rate of reaction. We learned the two major factors. One was the dependence of rate on concentration and second was the rate expression and rate constant. Now in today's video we will learn about the order of a reaction, molecularity of a reactions. Then we will also learn about this integrated rate equations and we will understand what is a zero order reactions. So talking about the order of a reactions. So let's go back to the rate equation that we did in previous class. That was rate equals to K, that is a rate constant, concentration of A raised to X and concentration of B raised to Y. Here X and Y, they indicate how sensitive the rate is to the change in concentration of A and B. Now the sum of these exponents, that is X plus Y, in this equation gives the overall order of a reaction, whereas X and Y, they represent the order with respect to the reactants A and B respectively. So if we have to define what is order of a reaction, it is simply the sum of the powers of the concentration, that is this addition of this X powers and the Y powers of the reactants in the rate law expression. Now this is a rate law expression. In this, when you add this X and Y powers which are there, that gives us the order of the chemical reaction. Now order of a reaction can be 0, 1, 2 or 3 and even a fraction. A zero order reaction means that the rate of reaction is independent of the concentration of reactants. Now if the reaction is said to be zero order, what does it mean? That it is independent. The reaction rate of the reaction does not depend on any of the concentration of these reactants that are present. A balanced chemical equation never gives us a true picture of how a reaction takes place, since rarely a reaction gets completed in one step. Now the reactions which are completed in one step, they are known as the elementary step. Okay, when a sequence of elementary steps, as in we are having multiple elementary steps like 1, 2, 3, 4 or maybe 5 steps, in that case such reactions are known as complex reactions. Now these may be consecutive reactions. Example is oxidation of ethane to CO2 and H2O passes through a series of intermediate steps in which alcohol, aldehyde and acids are formed. So this becomes an example of a complex reactions. Whereas if we look at reverse reactions and side reactions, example nitration of phenol yields of O-nitrophenol and P-nitrophenol. These all come under these complex reactions. Units of rate constant. Now what are the units of this reactions? For a general reaction, say AA plus BB giving a CC plus TD. Now you know that the small a, b and c, they are the stoichiometric ratios that are present, and these a, b's are the reactants and cd is the product. So rate we write as K, that is rate constant, A raised to X and concentration of B raised to Y. So if you do X plus Y, we will get the order of the reaction. Now this K which is there, if we rearrange this equation and get these two terms, they are in multiplication. So if you get it down here, it will be going to the division part of it. So we can write it as concentration upon time into 1 upon concentration raised to n, where A equals to B. Now if you look at the SI units of these concentration, it is mole, liter inverse and time, that is in seconds. So the units of K for different reactions are given below. So for zero order reactions, it is mole, liter inverse, second inverse. For first order reaction, it is just second inverse, because this one and this one will get cancelled. So we'll get finally 1 upon S. So S, if you take in the numerator, it will become S inverse. Second order reaction, again this one and this square will get cancelled. So we'll have mole inverse, liter and second inverse. Now let's next talk about another factor, that is the molecularity of a reaction. Now another property of a reaction called a molecularity, it helps in understanding the mechanism. What are the steps that are taking place in the reaction is what is defined by the molecularity of a reaction. So the number of reacting species that take part in an elementary reaction which must collide simultaneously in order to bring about a chemical reaction is called a molecularity of a reaction. So it is basically defined as how many species are reacting with each other, how many of them are undergoing the collision so that a new product is formed and to bring about a chemical reaction. That is known as a molecularity of a reaction. The reaction can be unimolecular when one reacting species is involved. For example, we talk about decomposition of ammonium nitrate. So here we see we have ammonium nitrate which then breaks down to give us nitrogen plus 2 molecules of H2O. So it is a unique molecule. We are starting with only one molecule of ammonium nitrate. Further, if you look for a bimolecular reactions involving in this will have two collisions that will occur simultaneously. Example would be dissociation of hydrogen iodide. So in this we are having two molecules of hydrogen iodide which are then colliding with each other to form hydrogen gas plus iodine. Same way we have trimolecular or teramolecular reactions in which three reacting species will be simultaneously colliding with each other. For example, we have nitrous oxide, 2 molecules of nitrous oxide plus oxygen giving us 2 molecules of nitrogen dioxide. Now the probability that more than 3 molecules can collide and react simultaneously is very small. Okay, so in that case what we do is that for such reaction molecularity is very low and therefore it is very rare also. It is therefore evident that complex reactions involving more than 3 molecules in the stoichiometry equation must take place in more than one step. So basically what we are saying here is that when we have molecularity, molecularity can be only defined for elementary reactions and not for complex reactions. In that case, because more the number of reacting species, more collision, and therefore the chances that all of them are going to collide with each other is very slow and is very low. So in that case what happens, the reaction rate automatically decreases. So this reaction, which apparently seems to be of 10th order, is actually a second order reaction. Now this shows that this reaction can take place in several steps. So if you look at this reaction, if you look and try to add on to the powers of each of these, it seems to be a 10th order reaction, but it is actually a second order reaction. Now if we are saying that it is a second order reaction, means it is having several steps that are taking place, out of which only maybe one step is of importance to us and the rest aren't. So which step controls the rate of overall reaction? So the question can be answered if we go through the mechanism of reaction. For example, chances to win the relay race competition by a team depend upon the slowest person in the team. So if we now want to define which is that step that tells us about the order of a reaction. If there are 10 steps happening, not all 10 steps are going to contribute to the order of the reaction nor the molecularity of the reaction. There will be only one step. So that one step, how do we define which one it is? So if we take an example of a relay race occurring, in that on what basis do we decide that is this team going to win or lose? So in that case what we talk about is the slowest person. Now if the slowest person continues to run at the same rate, then obviously you all are going to lose the race. But if the slowest person tends to put his 100% and give his best, in that case we have the chances of winning. So therefore it automatically depends on the slowest person in the team. So in the similar way, overall rate of a reaction, it is controlled by the slowest step in the reaction, that is called as the rate determining step. Now if we consider the decomposition of hydrogen peroxide, which is catalyzed by iodine ion in an alkaline medium. So if you have hydrogen peroxide here, we have iodine and it is an alkaline medium. So it reacts to give us water plus oxygen. Now if we write the rate reaction for this reaction, we can say that rate equals to minus T H2O2 upon dt, giving us K, that is the rate constant, concentration of H2O2 and concentration of I minus. So this reaction is first order with respect to both H2O and I minus. So evidence suggests that this reaction takes place in two steps. So first step is what? Hydrogen peroxide plus iodine, they give us water plus IO, and the second step that gives us hydrogen peroxide plus IO, giving us water, iodine and oxygen. Now both the steps in this case are bimolecular elementary steps. Species IO is called as the intermediate since it is formed during the course of the reaction but not in the overall reaction. If you see, it is formed in between but it is not there in the final reaction. The first step being the slow is the rate determining step. Thus the rate of formation of intermediate will determine the rate of the reaction. Now from this we can conclude three major points. First is that the order of the reaction, it is an experimental quantity. It can be 0 and even a fraction. But when we talk about molecularity, it cannot be 0 nor can be it a non-integer. Non-integer is it cannot be a fraction. Second, the order is applicable only to the elementary as well as the complex reactions, but the molecularity only sticks to the elementary reactions. For complex reaction, molecularity has basically no meaning to it. So for complex reaction, order is given by the slower step and molecularity of the slower step is the same as the order of the overall reaction. So that was about the factors that affect the rate of a reaction. Now let's look at the integrated rate equations. Now we have already noted that the concentration, it depends on the rate called the differential rate equation. It is not always convenient to determine the instantaneous rate as it is measured by determination of the slope by drawing tensions at point T in concentration versus time plot. Now this makes it very difficult to determine the rate law and hence the order of the reaction. Now in order to avoid all of this difficulty, what we do is we can directly integrate the differential rate equation itself so that we get a relation between the directly measured experimental data, that is the concentration at different times at rate constant. Now let's look at the first integrated rate equation, that is the zero order reactions. Now zero order reaction means that the rate of the reaction, it is proportional to 0 power of the concentration of the reactants. So what we had said for zero order is that the rate of the reaction is independent of the concentration of the reactants. Now let's see how is that. So we have reactants giving us product. If I write the rate equation for this, rate will be equal to minus T concentration of R upon dt, that will be equal to K and reactant raised to the power of 0. Now anything raised to the power of 0 is said to give us 1, that is unity. So rate will be equal to minus dr upon dt equals to k into 1. Now dr, if I rearrange this equation, I will get this dt, I'll take here. So dr along with this minus sign, I'll take it here. So dr will be equal to minus k dt. On integrating, this differential will go off. So we'll have concentration of R will be equal to minus kT plus I. Now this I is basically the constant of integration that we add. So now let's consider at time 0, the concentration of the reactant R is equal to R0, where R0 is the initial concentration of the reactant. Now substituting this in the above equation, what do we get here? We substitute. So here in this case, if we substitute, we'll get R0 equals to minus time we have said at 0, so 0 plus I. So R0 will be equal to I. Now substituting this value of I in equation 3.5. So in this value, we substitute this I as R0. Now if we compare with this equation, so this is in the form of y equals to mx plus c. So my slope is what? Minus k, and on the y axis I have the concentration of R and the x axis I have the time. So I will get a plot with a straight line with a slope minus k. On y axis concentration of R and x axis we have the time. Now on further simplifying, we can find the rate constant k as R0 minus R upon T. So for zero order reactions are relatively uncommon, but they occur under special conditions. Some enzyme catalyzed reactions and reactions which occur on the metal surfaces are some examples of the zero order reaction. The decomposition of gases of ammonia on a hot platinum surface is also an example of zero order reaction only at high pressure. So in this reaction, if we look, we have ammonia, platinum catalyzed it gives us N2 and 3H2. So if you write the rate of the reaction, K will be NH3 raised to 0 equals to K. In this reaction, the platinum metal this metal catalyst that is there, it will act as the catalyst. So at high pressure, the metal surface gets saturated with the gas molecules. So a further change in reaction condition is unable to alter the amount of ammonia on the surface of the catalyst, making the rate of reaction independent of its concentration. So the thermal decomposition of HI on gold surface is also another example of zero order reaction. So that was it for today's video. I hope you have understood. Please don't forget to like, share and subscribe to the Academy.